Welcome to the lecture series of Fourier transform. In this lecture series, I am discussing about the Fourier transform. In this video, I will basically discuss how to determine the input-output relation and the transfer function of a electrical system. In this lecture, I will discuss about the RC circuit. So the first thing we need to know that how actually we determine the capacitor current and inductor voltage. So in that case, if a capacitor carries a current I, and for that current, if voltage is built like this fashion here, plus and minus, and as we know, when the currents in to a particular point, that point should be indicated by plus sign for the voltage, and the terminal where the current out, that portion of the voltage will be marked as negative. So what would be the law to determine the capacitor current? The capacitor current is nothing but the C dV by dt. So with the change of time, the voltage, the changing of voltage, these two ratio actually determine the current through the capacitor. In the similar fashion, if we need to determine the voltage of an inductor, so nothing but the voltage at the inductor is multiplication of L di by dt, where I is the current is passing through the inductor. This is the indication of current inserting to the inserting to that point. Actually, that point basically the voltage across the inductor positive terminal. So by this basic law, we can determine the capacitor current and inductor voltage. So if you are being asked to, if you are asked that this is the RC circuit and you need to determine the output and input relation, or sort of transfer function, so what would be the procedure? So in that case, yt is the output, and basically it is the voltage across the capacitor. So how could we determine the voltage across the capacitor? We should apply this law. So basically these equations are same, because when we have to determine the voltage, actually after taking the integration of both sides, we actually get the voltage across the capacitor. So if we recall for this law for either for capacitor or current or capacitor voltage, we can use this law actually. So in that case, we need to have the value of voltage of the capacitor. Actually in that case it is yt, so yt can be written 1 divided by C integration of it dt. I think it would be very easier for you. So our ultimate goal is to formulate a equation containing the input and our output. Here the xt for input voltage, yt for the particular voltage at a capacitor. In that for that system, the yt is the output of this system. Okay. So if we consider the current direction for this resistor, the voltage polarity of the at that terminal, voltage polarity of that terminal would be positive, here the negative. So if we apply the Kirchhoff's voltage law at this slope, we will get minus xt plus ir and plus yt basically. So yt can be written like that. So this is the Kirchhoff's voltage law for this loop, and our ultimate goal is to determine the xt. So so xt can be written from this equation. So what would be the output? So actually this is the output, and the if we need to determine the transfer function, we need to take the ratio between the output and input. Here the input is xt, so if we take the Fourier transform, we will get the input in frequency domain actually. So this is the Fourier transform of integration part. You can check the Fourier transform list in any textbook or online. You will get the Fourier transform of integral part is like that. So just dividing by j omega. Okay, so as in differentiation we have discussed that taking the Fourier transform of any differential part, just multiplication is needed to with the x omega, that means x omega is given by the Fourier transform of xt. So in that case, if we need to take the Fourier transform of any integral part, we just need to divide the with the j omega. So this is the case, this is the procedure. Okay, actually. So in this line we can represent the input in frequency domain of the system x omega, and for having the transfer function of the system, actually h omega is the ratio of input and output in time frequency domain. So basically this is the input, and output is given by here. So taking the inverse, taking the Fourier transform, we will get the y omega. So to have the transfer function, actually the ratio of output and input. So this is the this term and this term we take just inserted here instead of y omega and x omega, and ultimately after calculating we will get 1 divided by 1 plus j omega rc. So if we are if you have to determine the impulse response, as you know, as you have solved in previous lecture, I discussed about the impulse response and transfer function. So as you have the transfer function here, if you have to determine the impulse response, just you need to take the inverse Fourier transform of that. And this is nothing but if in a fashion like 1 divided by alpha plus j omega. We have determined several time in previous videos or in several lecture, in several problem we solved that. So taking inverse Laplace in this fashion, as I have said for this. So this is the inverse Fourier transform of that. So it is our ultimate goal, where you can determine how in this way you can determine the value of impulse response of the system. So basically this type of question, in this type of question you will be asked to determine the impulse response of the system. The first step would be determine or recall this relation, the capacitor current and the inductor voltage. So in that case, fortunately this is only simple first order RC circuit. So here, after having the Kirchhoff's voltage law, you will get the input, and taking the relation either inductor or capacitor, you will get the output, and from these two you will get the transfer function, taking the ratio, and taking the inverse Fourier transform, you will basically get the impulse response of the system. Thanks for watching. In this video I have tried to present how to determine the impulse response of a RC circuit.